Uh, Welcome back, and let's get started with our class. Okay, today we'll talk about data abstraction. And in the data abstraction, we'll try to learn more about the main concepts of data abstraction and how we can apply that within our uh, context. First, let's learn more about what we mean by data and what are the different types of data, and then we will see some examples about data and how they can be used. Initially, what does data mean? Data only becomes meaningful when we understand its context. And this is exactly what we wanted to highlight on in here. Now, what we wanted to highlight exactly is when I have data, like for example, I have numbers, so the data may not have a meaning, and the meanings are not clear. So until I do have a context for this data. So this is the data context. So I need a context. Like for example, if I'm looking at numbers 1, 5, 7, 10, do you mean temperature? Are you talking about distance? Is this, for example, weights? So what exactly is the context of these numbers? And this is what we will learn about is the context of our data. What do you mean by certain data? So the same numbers can represent entirely different concepts, depends on how we interpret them. As I mentioned, it depends on what the data is representing and what's the context of the data. The same numbers may have different meanings. So we wanted to learn about these meanings and see what's the meaning of each one. From coordinates in space to network parameters to scientific measurements. So the data will differ based on the context. As scientific measurements, these numbers could reveal complex patterns, or they might define connections between handwriting vulnerabilities, or they applied in space, they could represent specific coordinates within the sky. So let's see an example. In this example, we are looking at numbers. I'm looking at 14, 2.6, 30, 30, 15, and 100,000. So these are 6 different numbers, and these numbers may have different meanings. What does this sequence of 6 numbers mean? Without a context, we simply cannot know. What's the meaning of these numbers? We do not know. Now, until I have specific context that will tell me exactly what the data means in here. So the same data could represent completely different concepts across various domains. So the meaning of this data can be different, depends on where I am using it. Coordinates in space, perhaps these are 2 points. For example, if I'm looking in the context of coordinates in space or network parameters, or even something entirely different than these two. If I look at coordinates in space, perhaps these are 2 points in three-dimensional space. So this is like, for example, 14, 2.6, and 30. These are in 3D. I'm looking in 3D coordinates. So this is a point, and this is a second point. This is possible, and they could represent locations in virtual environment, or they are astronomical positions, or they are molecular structures. So they do have different meanings if I look at them in coordinate space. I'm combining them in triplets, 3 numbers each. Or if I'm looking at them in the context of network parameters, this might describe 2D graph with specific properties, like for example, 14 and 2.6 are node positions, 30 as a connectivity measure. So I'm looking at this is the first one, this is the second one. This is 14, this is 2.6, and the connection between them is 30. And 15 as the number of links. So there are 15 links between them. And 100,001 as the weight in particular connection. So you can see in the context of coordinates is totally different or totally different than network parameters. Something entirely different. So these numbers could also represent financial data. So I'm looking at profit, sales, how much sales I have across years, for example, or scientific measurements, or some sort of measurements like a pressure or temperature or humidity or specific measures in science, time series values, like some values across time, or countless other possibilities. So the point is clear now. This data requires to have context, to have more meaning. Unless I have a meaning, I won't be able to tell what exactly the meaning of these 6 data points. So the same sequence of numbers could describe physics, geometry, social networks, or completely unrelated domains without context. The interpretation is almost impossible. Okay, now we learned about this data. Let's see other examples. Could these numbers be coordinates, network parameters, or just random measurements, or even other things that that we do not know? Without the context, we cannot tell. We looked at it in the form of or in the context of stocks. It might be a price for stocks over time or patent vitals. So I'm looking, oh, sorry, patients vitals. You're looking at respiration rate is 14 or blood pH or heart rate or temperature. So I'm looking at patients, people like they're in the hospital, they are sick, they are not feeling well, and we are measuring their vital information. Or it can be some sort of Internet of Things sensors coordinates, some information about data, about, sensors. We are collecting information like pressure or altitude or longitude or something like that. Now, the thing that we need to know, context is important, and we cannot do anything with the data without learning what the context of the data is. So now context defines everything in terms of the data. For example, I'm looking at a second example. So example 2. So this is second example. I'm looking about Basel, 7, S, and pair. So what's the meaning of these 4 variables? We do not know. We need some context. Let's see. Even with this seemingly descriptive words, even though we do have some words in here, but does this give us a context? No, we do not. So multiple stories can be constructed from the same data set. So we can tell multiple stories from this without context. Consider how different fields might interpret this exact same data. So let's look at these 4 data points and see them. And these are 3 contexts, context 1, 2, and 3. So we added 3 different contexts, and let's look at it. Basil and pear, they are food items. Basil, it's like basella, and pear, they are food items. They arrived on the 7th day of the month. So they came at the 7th day of the month. So we're talking about we are in March. Let's imagine we have received them in March 7th of the month. The letter S indicates that satisfactory. We are happy with this delivery. So they have reached their destination on time. So this is something that we can interpret these results with. Let's look at it from a different perspective. City services. Basil Point. So Basil Point, it can be a location, street name, or like a city or a town. Had 7 inches of snow. So they received like 15 centimeters of snow. Uh, Cleared. So now we are talking about 7. This is a measure of snow. The height of how much snow would they have received by Pier Creek Limited. So this is another location, a company name, a contractor, a company name that removed the snow with S representing the south district, so south area, and Pier Creek Limited is the company that will remove the snow. Now, Basel in here, it tells me this is the location. Pier, it means like the name of the contractor. S, it means the south, and 7 is the height of the snow. So now you can see the same 4 variables or values, constants that we have in supply chain. They have a different context than what we see it in a city service. Or we can see them even in a different domain when we talk about lab results. Lab research, we have a laboratory rat. The name of the rat is Basil. Completed 7 successful mazes. So mazes like puzzles. So they run from, these are the mazes. So you can see they moved in these mazes. They run in the south. They started from the south, selecting a section of the facility, using a pair as a reward incentive. So they feed him pear as an incentive, rewarding, just to encourage him going from one location to another. Now, in the three contexts that we see in here, the meaning of these variables is different. Now, this gives us how important the data, that the context is for our data. Now, when we look at the data itself, we wanted to see what are the basic building blocks. So the basic building blocks of our data. We talk about items and attributes. So let's try to differentiate between items and the attributes. At the core of all data lies the concept of items and their associated attributes. Like I do have an item, each item has set of attributes. Understanding this fundamental relationship is crucial, is extremely important for creating, for structuring, and translating, interpreting, understanding any data. So let's see. What do we mean by item? The item is any distinct entity, any unique entity or object that we want to collect data about. So let's say I wanted to collect data about patients, about cars, about cities, about students, about university, about a specific location. So these all are items. It could be a person, a human being, a student, a patient. It can be a product. I wanted to buy a shirt, pants, a car. It can be a location, a specific city, district, country, or a specific event like a snowy day or 4th of July or a specific holiday or Eid and so on and so forth. So we call all of these as items. Now let's look at the attribute. Attribute is the characteristic, is a characteristic or even a specific property or properties that can be used to describe an item. For example, if I'm looking at product, I'm looking at shirt. So this shirt, it does have material, it does have a color, it does have, so the material, the color, the size, all of these are attributes. The shirt itself is an item. Describe an item. Attributes to provide specified details and measurements. So I'm talking about the details such as color. Measurements like the size. The size is medium, large, X large. That gives context to an item. That will give me a context that can be using to decide. I can use it to decide what exactly that item is. Now let's look at some examples of items and their potential attributes. Like for example, I'm looking at a patient. The patient is the item. Remember that we said person is an item. Some of the characteristics in a healthcare data set, I'm talking about patient in a healthcare system, their attributes might be age, how old they are, blood pressure, heart rate, or medical history. So now all of these are attributes for the patient, which is the attribute, the item. Now a second example of an item is car. Now the car in this example is an item uh, on automotive data set. The attributes that could be, for example, the horsepower, how many horsepowers this car is. Fuel efficiency. So we are looking about how much you can drive this car on 1 gallon of gas. A make, like for example, this is Honda. Model, it's a Honda CRV, for example. The year is 2024. So all of these are attributes that are describing this item that's called car. Another example, we are looking at a city, like let's say we are looking at Irbid. This is an item, the city. A demographic data set. Its key attributes might be include population, how much the population is, like let's say 2 million. The population, the area, like how many square meters, average income, how much is the average income, people, how much money they make per year, for example, on average. The major industries, do we have like agriculture? Do we have more of shipping, exporting and importing, and so on and so forth? So all of these are attributes of the item city. Now, the basic building blocks, as we said, the items and attributes, the data, when data is organized, each row typically representing an item. So this is a patient with all of its information. So this is an item. and each column representing an attribute. So you have, these are the attributes that we have for each column of that item. Now, you can see in here we have a patient, age, blood pressure, heart rate, and so on and so forth. Think about a data set you work with in like insertion assignments, for example, and you can differentiate between attributes and items. Now, let's look at another example, like more of visualization, how I can visualize items and attributes. For example, person is an item. This is something that we learned in the previous example. Let's examine a concrete example, an actual example where each person is an item. So I do have individuals in here. I have Amy, Basil, Clara, and so on and so forth. I have Amy, for example, and we can track four attributes of each. We can look at their name, this is attribute one. We can look at their age, attribute two, shirt size, and favorite fruit. So we have name, age, shirt size, and favorite fruit. Each one of them is an attribute. So now we have one item. Amy does have, the name is Amy, 12 is the age, medium is the shirt size, and she likes orange. In this visual representation, each vertical column, so these are the vertical columns that we have, they are representing one person item, like what you see in here. While the horizontal row shows different attributes for this person, this structure forms the foundation of how we organize and analyze data systematically, in a systematic way. Now, we looked at the data in more of tuples. If you remember this in the database class, we call them tuple. Now let's look at it beyond just the simple pairs, just two of them or couples, beyond just simple pairs, other data types. While items and attributes form the core, like items and attributes, they are the main things within many data sets. In real world, data often includes additional structural elements that captures the relationship, positions, and other patterns. Let's look at, for example, links. Links express relationships between two items. Like, for example, I can say this person and this person, what's the relationship between them? Or I can look at fruit and apple, what's the relationship between them? Creating a network of connections. It might be also other connections, like this is not just a single two or two connections. Examples include friendship on social media. So you are on Facebook, you have all of your friends connected with you. So you will see that those people are connected with each other. And this connection will create what we refer to it as a community. Interconnections between, like this is an example. Another example is interaction, connection between proteins in biological system. I have proteins and I know the functionality of each protein. And some of them, they have multiple functionalities together. So this protein, for example, does have two functionalities. Or even citation between academic papers. Like if I have, for instance, a paper that talks about natural language processing and other person is citing this. So most likely those people are interested in the same domain. One other thing is position. Spatial data captures locations in 2D or 3D. So I'm talking about like position within a map or an image, either 2D or 3D. This includes pixels in photographs or voxels in MRI scans, like this is a medical images, or latitude and longitude when we are talking about coordinates on Google Map, or any data points with physical position information. So I'm talking about the position, and the position sometimes is showing relationship, especially like I'm talking in map. I do have two cities next to each other, two positions. So they do have longitude and latitude that they are representing the data. Now let's look at the grid. Grid, think about it like rows and columns. So this is called the grids. The grid represents sampling strategy for continuous data, dividing spaces into regular cells. Like for example, I'm just selecting this area or this area or this area. This approach is essential for representing phenomena, like phenomena that happen at a certain point, like temperature across regions or elevation across terrain. So when we talk about temperature, I'm looking at areas, like for instance, these areas they have the same temperature. Or I'm looking at regions, and I'm seeing how much is the elevation. Elevation, that means how high they are from the sea level, for instance. So now these are not just the simple pairs of information. We are looking at much more complicated relationship. Now, let's look at the data in the form of a flat table and how can we read this information in a flat table. So the most common straightforward data set structure is just going with a flat table, rows and columns as we see it in here. This format organizes data in a simple, intuitive, just very simple, intuitive, you can understand it by default, way that forms the foundation for data analysis. Like it's the basics, the main things that we can use for analyzing and understanding the data across countless fields. So you can use it in biology, chemistry, computer science, and medical school, and pharmacy, and others, countless number of fields, no matter what field you are using it in. Now, the structure as we see it in here, one item per row. So we're looking at one item, one person in this example. Each column represents attributes. So these are the attributes that we have. Each column is an attribute. Each cell holds a value for that item attribute pair. So this value is for Amy, the person, and the value for attribute shared size. So each cell holds the value. The value in here is M for the item. In my case, the item is Amy, and the attribute is shared size. Include a unique value sometimes implicitly. So we do have a unique value in here, which is the ID. Sometimes it's implicit, it's not explicitly listed in here. For example, in this table, we have seen name, age, shared size, favorite fruit, and we have seen them in the form of flat table. Flat table are ubiquitous in data science because they are easy to understand. They are important because they are easy to understand. They are easy to manipulate, to process, to deal with, work with. You can use Python code easily to deal with it, easy to analyze. Spreadsheet like Excel, for example, applications can be used to deal with it. Database, SQL, and statistical software, SPSS, for instance. All they can use this fundamental data structure, which is the table. Now, let's highlight a little bit and look at it again, the table. So the anatomy, the details of the table. Um, we said we have an item. We have this is a cell. This is an attribute, and the cell value would be like medium box, for example. Now, if we look at each of these tables, you may have a header row. So this is the first row, is a header row, just contains some information to identify what each attribute is. It's a descriptive, it's just describing what each column contains. Data rows, so these are the rows that we have. And then we have the cells, which is the intersection between rows and columns, and they contain values. Now, sometimes what happens is this information, I wanted to represent it in more detail, so I cannot just represent it in 2D or something that we call flat table. So I wanted something more advanced to represent my data because I cannot just show it in this flat table. And this is what we have done. We are looking for multi-dimensional tables or multi-dimensional tables. So we're looking about tables that are stacked on top of each other. As you see it in the right bottom in here, we are trying to show multiple tables and they are stacked on top of each other. So you see this is 1, 2, 3, and 4 tables, for example. Now we do have the flat table and we do have multiple versions of this flat table. And this is what we refer to as multi-dimensional tables. Now, in these multi-dimensional tables, when data becomes more complex, data is not as simple as just rows and columns. We need specific structures to go beyond just simple uh, flat tables. We need something that's more of multi-dimensional tables to use multiple keys to index the data. So now I cannot just go and look at the data by looking at this ID. No, I wanted to know which table it is, and in the table, what's the ID within that table, which will enable more sophisticated analysis of relationship between these different dimensions. So I'm looking now about more tables and the index within that table. So this structure of multi-dimensional table uses the index based on multiple keys simultaneously. So I'm not just using a single key. For example, you might index the data beyond by both genes and patients. So I wanted to find out in chromosome number 5 for patient number for patient number 1, 2, 3. So you have patient 1, 2, 3, and what's the gene that you are looking for, or what the chromosome that you're looking for, which will create like a big matrix, and where each cell represents an expression level of that specific gene in a specific patient. And this is what we have done. So we do have the genes and the patients, and we have them in this is like think about it like each patient is an Excel sheet, and we have 5 patients. So we have 5 patients, 5 Excel sheets, and each Excel is representing the genes information for that patients. So we have multiple independent keys, like genes versus patients. So you can identify first the patient 1, 2, 3, 4, 5, and the gene, which is the row, or vice versa. Values are at the intersection, or intersections represent the relationship common in scientific research and business intelligence, and they enable complex queries across multi-dimensions. Multi-dimensional structures are powerful for analyzing patterns across multiple categories simultaneously, such as sales by product. So you're looking about how much you are selling by product. For example, I'm looking at iPhones and how much I am selling iPhones in Irbid, in Amman, in Aqaba. Time period. So I'm looking in January, February, how much I'm selling in Irbid of these iPhones. Or for example, I'm looking at gene expression. Like um, gene expression means in here, like you do have a specific eyes color, the colors of your eyes, and you wanted to find out how much expressiveness they are. So they will have a specific value in different patients and with different conditions. Like for example, you might look at it for specific patients with cancer. How much is the expression value of a specific gene? Now, we looked at the data as simple as single table, then a flat table, then we stacked set of tables on top of each other, which created a little bit more complicated and sophisticated data structure that can be used for representing more complex data. How about if I wanted to represent the data differently? Like this is the table. Now this is 3D table. Now I wanted to look at it in terms of relationship, which will construct what we call a network or graph. Now networks and graphs, they are a bit more complicated. You can see I do have network or graph. Remember the tree is a special case of a graph, as we have learned more about it in data structures and artificial intelligence. So network data structures captures relationships and connections between items. So I have patient 1, for example, and I have patient 2, patient 3. They have the same age, patient 1 and patient 2. Patient 3 and patient 1, they do have the same disease. Patient 2 and 3, they have the same age and the same disease, for example. So I do have like more of connections between items, revealing patterns that tables cannot easily express it. Like for example, if I'm using the tables to represent sales across cities. I'm looking in Erbil, in Amman, and Madaba. So I do have 3 different cities. I'm looking in between them. If I look at tables or even 3D tables, it will be very hard to represent this relationship. Now I need more complicated, sophisticated structure that will help me represent this data. One of the data structures that I can use or representations would be networks or graph. These structures are fundamental to understand social systems like Facebook, LinkedIn, biological process or processes like cancer and others. And they can be important for information flows. Network structure consists of nodes. Remember that we have nodes and we have links. We call these nodes as vertices and connections. They are connected by these links. Also, we call them edges. This structure naturally represents a relationship. So by natural way, it's showing me relationship, friendship, and social networks, for example, chemical bonds between molecules. If I have H2O, for example, what's the relationship between them? Or web pages linked by hyperlinks. If I have, for example, a specific university's website connected to the government, so these are represented by this is a node, this is a node, and this is a hyperlink between them. Now we know network or graph, they are the same. like different terminologies. Uh, Special type of graph is tree. And remember, the tree is what you see in here. The tree is each node has only and only one parent. And this is the like it's a graph with each node has only and only one parent. We call tree. So trees are network with no cycles also. They do not have cycles. You cannot follow links and return to where you started from. That means it's a cycle. So if I start with a node, I cannot go back to this node. If I have this relationship that I drawn in here, that means this is a graph. If I remove this, it will become tree. Tree often have a root. So it does have a root, and either directed or indirected are directed, making them ideal for representing hierarchies. Hierarchies, when I talk about hierarchy, I'm talking about the relationship of sub and super class, child and parent. Like organizational chart. When I talk about organizational chart, for example, I'm looking at the president of university. Then I do have the dean of a specific college. Then I have chair person of a specific department, and I have professors and students. So this is more of hierarchy, hierarchical relationship, an organizational chart, or file systems. Like when I look at C drive, within the C drive, you have folders. Within each folder, there are folders. This is what we refer to as file systems. Now, we have seen flat tables, multidimensional tables, the network and graph, and the next data structure that we can use, or next representation, we will refer to it as spatial fields. Now, spatial means points that have a relationship between each other, like something similar to map or image. So this is what the relationship between them, we call it spatial fields. Now, spatial data represents continuous phenomena across geographics or physical space. Now, for instance, if I look at this is United States map. So I try to look at locations. So if I zoom in, I can see there are some blue dots in here. That means they have, for example, similar um, I don't know, urban, or they have like they have park urbans or rural. So they do have certain, the nature of them is different. Like let's just call it, some of them are cities, towns, and so on and so forth. So they are in physical space, unlike discrete data points. So when I talk about discrete data points, I'm talking about, for example, your temperature, your blood pressure for 5 patients. Spatial fields, they capture how values change smoothly. Like the temperature in here is 35 Celsius. Now, if you move in here, you will find it's 36. Then you move in here is 38. So this is it's moving smoothly. Uh, the opposite of that, if you are in here 35, all of a sudden it's 75. So this is not smooth. This is a big jump. Now we talk about the regions that are next to each other, and the change is moving smoothly across these regions, making them essential for scientific and geographical analysis. So if I try to understand and learn more about the geographical area in here, so spatial fields are key for me to learn more about this and represent the data. So the data can be continuous values. Spatial fields contains attribute values associated with cells or points in a space, like the temperature or pressure. Each cell holds a value from a continuous domain, which is the temperature in this case, such as temperature, atmosphere, pressure, or elevation. Elevation is the height from sea, or even wind velocity, like the speed of wind in a specific area. The data source or data sources, the values in spatial fields may come from measured data like weather or station readings. Like if I do have a station that reads the temperature, every day, every other hour, for example. Simulated data, sometimes it's not real data, it's data that you created from simulation, like climate model output. Both sources are valuable for different analytical purposes. So both of them are important and they can provide me with the specific information. Now we have learned about different types of information and how you can represent the data. Each one of them will carry different types of information that can be used for different type of analysis. Now, thinking about spatial fields, what are the key considerations when we are learning or using or dealing with spatial data or spatial fields? Work with spatial data requires careful attention to three fundamental questions that determines how accurate and efficiently or effectively, sorry, we can represent continuous phenomena. For example, sampling. How do I create sampling? Where do I create sampling from? Interpolation, grid type. Now sampling. Let's assume you are trying to read temperature, like weather temperature. You are going from Erbil to Amman to, for instance, Salt, Maraba, and then you go to Aqaba. So you have four different regions. So where do I read the temperature? Do I read it in here, in here? Like what's the distance between them? How can I read the temperature? So this is the sampling. Sampling addresses where data values are collected and measured in space. So do I measure like every like 5 kilometers and measure the temperature? Or every 10 or 15. And so it's critical to ensure the spatial finds accurately representing reality. So it's representing reality. Poor sampling can miss important variations. Like for instance, if I decided I want to go and measure it every 100 kilometers. So I measure it in here, then in here, then in here. So I'm not measuring the data as I should be measuring it. So I'm missing a lot of information in between. So you have to be careful or introduce bias in your analysis when you are measuring it differently. So this is the first part, sampling. The second one is interpolation. Interpolation, that means, like, let's assume, let me just delete this one. I have five different regions, and these five different regions, just look at this number of them, R1, R2, R3, R4. Let's just go with four different regions. Now I'm trying to measure the temperature between these regions. So I measured 5 kilometers and I measured like T1, then T2, T3, T4, and so on and so forth. Now, this is at 10 kilometers. So I just went 10 km. This is 20 km. Now, and then I measured this one at 0 km. Now, the temperature between them at 5 km. So at 5 kilometers, what's the temperature in here? So how can, if I measure this as 30 and this is 35, what's the temperature at 10 kilometers in between them? Now, to predict what would be the value or try to infer what the value between them, we call this as an interpolation. And then I went at 20 kilometers, it's 36. So in between, I have values. What are the values? I need to find out what the values are. This is what we refer to as interpolation. So I wanted to find out, deal with how to estimate. Now I'm estimating the value between like 0 and 10. How to estimate values at locations between or beyond the measured points, like 5, 10, and 15. This is necessary because we cannot measure everything and everywhere. We cannot measure it everywhere. Mathematical techniques, they will fill these gaps to create continuous field from discrete measures. So there are methods. So first, sampling, two is interpolation, and three, grid type. So now I'm creating a grid when I'm measuring these values. I wanted to know what the type of grid. You need to examine what kind of layout organizations, the space. In our case in here, we are measuring linear distance. I'm not just I'm measuring like, for example, like if I wanted to go from Erbil to Amman, like you might go like this, or you might have a straight line, or you want to have this, or you might have a line like this. So what's the exact grid type? Am I looking at the straight line, or I'm looking at, like for instance, the street that I can take from one route to the other. So you need to find what kind of layout organizes the space. Different applications benefit from different grid types. Like if I'm measuring, for example, the air distance is different than if I'm measuring the actual distance between the two locations. Regular grid for simplicity, hexagon grid, for example, for uniformity, neighborhood, or irregular grids that adapt to specific terrain. And this is an example where you have a grid in MRIs, for example. You are taking some medical images. Now, the data representation is extremely important. In spatial, for example, it does carry a lot of information. We need to learn more about how to create a layout. And this is the layout that we are creating, the grid, the interpolation, sampling, and certain parameters that are key considerations when we are thinking about spatial data. Now, let's take some examples when we talk about spatial data, such as sampling and interpolation. To effectively analyze continuous spatial phenomena like the temperature or humidity or like uh, the wind speed, for example, we must adjust how data is being collected, sampling, like distance, time, how missing values are estimated. Like if I'm collecting like every hour from like for instance 4 p.m. up to 5 p.m. I'm taking two data points. So how about 5:15 or 5:30? I do not know what the values are. I need to interpolate them. So these processes are crucial for creating complete and accurate representation of a specific area. For example, filling a gap. So you can use like to fill a gap, this interpolation, which is used to known data points to estimate values to unmeasured location. So you can interpolate it, just find the average, for example. The formula above represented the inverse distance weight, where each value, VI, from a nearby sensors are weighted, WI, by the inverse squared of their distance to estimate a new point. So if I wanted to estimate a new point V of X, for instance, this method can be used to interpolate missing air quality. I need air quality measure. Reading between cities like Amman and Erbil based on the surrounding monitoring stations. So I did not read the somewhere in between. So I need to estimate it and try to interpolate it. Now, grid type, organizing space, for example. A rectangular grid. A simple uniform grid, like I'm talking about rectangular, just very simple, where cells are square or rectangles, is ideal for a consistent sampling interval. Like I can go every other circle. I can sample in here, sample in here. For example, sample in here, sample in here. Now I created more of regular sampling. Uh, Curvilinear linear sampling is a flexible grid that adapts to complex geometric or physical boundaries, often used for irregular shapes or a fluid type of dynamics. So it can change based on the changes in the actual area that you are measuring in. Now, we talked about different types of layouts. Now let's look at the data itself. Now we do have scalar, vector, and tensor fields. Spatial fields can represent different types of data, different types of data points. Now I have cells. What are the values in these cells? Depends on the complexity of the information recorded at each point in the space. If it's a temperature, it can be a scalar, just single number. Or it can be temperatures for for example, minutes or 3 hours. So it can be vector, it can be all even more complicated. Understanding these distinctions is crucial, is important for selecting the appropriate visualization and analysis method that we can use to apply on that data. For example, scalar fields. Scalar fields assigns a single numerical value, temperature 55, blood pressure 104, and so on and so forth, to each point in space. This value describes a magnitude without direction. So I'm just saying a specific number. I'm just not showing direction. It's a single value per point, like a temperature or atmosphere pressure. Applications, like for instance, for meteorology, like temperature, pressure map, heat map, or heat distribution, or elevation on a specific map. The other one is vector fields. Vector, I'm talking about multiple values. A vector field assigns both a magnitude and a direction. So I'm looking at a specific value. Magnitude is what we have seen in the vector, or sorry, in the scalar, and I'm adding to that the direction to each point in space. It describes phenomena with movement or specific force. For example, I have magnitude and direction, wind speed, so and direction, flow the flow. So I'm talking about like the speed of wind is 50 miles per hour, and it's coming from east to west or west to east, and so forth. Application, weather forecasting, wind patterns, fluid dynamics, and magnetic fields. So these are some applications. So I'm talking about in the vector, it's not just a single value. We do have multiple values. Tensor field. Tensor field assigns multi-dimensional mathematical objects. It's an object. It's not just a single value. A tensor, which we refer to it as a tensor, to each point, capable of describing complex relationship like stress, strain, or diffusion and entropy. So, for example, I'm looking at my multidimensional value per point, like stress tensor or diffusion tensor. Application biomedical imaging, they are very popular. So these different types of fields, they allow us to model a vast range of physical and abstracted phenomena, providing a foundational for scientific understanding and data-driven insights that we can make decisions based on. And we have some examples in here that will show us the different types of data. Now, let's highlight the types of spatial data fields. So when we talk about spatial fields data, so spatial fields differ not only in where the data is being located, but fundamentally in what kind of data is stored at each location. So what's the type of data that we are saving, what kind of data we are saving. Understanding these distinctions is crucial for choosing the appropriate visualization and analysis method. So we learned about scalar, vector, and tensor types of data and how they are or they differ. In summary, just to summarize this section, we talked about different types of data or dataset types like flat, multi-dimensional network or graph and spatial data, the key characteristics and the common examples of each one. Thank you.